Swayam Prabha. Digital India. Educated India.
Now, in this lecture, we will discuss the kinematics of a particle. We have already studied kinematics of a particle, in which we obtained the velocity of a particle by differentiating its displacement vector, acceleration by differentiating the velocity vector. Now, in this lecture, we are going to discuss the effect of forces on the motion of the particle. In kinematics, we did not consider the effect of the forces. In kinetics, we will study the effect of the forces on the motion of a particle. The particle, due to influence of the forces, will change its velocity. There are four approaches to the solution of kinetics problem. A. Direct application of Newton's law. Direct application of Newton's second law. B. D'Alembert's principle. C. Use of work and energy. Work and energy. D. Solutions by impulse and momentum methods. Now, we discuss these one by one. First is the direct application of Newton's second law. It is the second law which is widely used in solving the kinematics problem. Newton's second law states the acceleration of a particle is proportional to resultant force acting on it and is in the direction of this force. So, this is a vector equation, that is F is equal to m, where m is the mass of the particle x scalar, but a is the acceleration vector. So, F is equal to m into a. We keep on using this law widely. However, the relation can be verified only experimentally. There is no theoretical proof that y f must be equal to mass times acceleration. Moreover, this law is not valid in all frames of reference. For this law to be valid, we have to assume the existence of a fixed primary inertial system. If we can assume a fixed primary inertial system, that is fixed primary inertial system, this is an imaginary set of reference axes that are assumed to have no translation or rotation in space. So, assume that I am having O is a point here, this is x, this is y, this is z. This axis system is totally fixed. It is the central point O does not move at all. X, y and z axis does not rotate at all. If we can find out such reference system, this is called primary inertial reference system. This system is, of course, will have to be called imaginary, because we cannot find out for sure a reference system which is not moving. If we are sitting in a room, we can draw the axis x, y, z. We will see that these axes are not rotating. However, if we observe outside the earth in the space, we see since the earth is rotating, therefore the axes are also really rotating. So, therefore, it is difficult to find out this thing, but for all practical purposes, we can in solving the problems of machines, we assume that earth can be considered as the primary inertial system. Now, this F is equal to ma is valid only in the, it's only valid in the primary inertial system. Newton's second law is valid in primary inertial system as well as with respect to any non-rotating reference system that translates with respect to the primary system with a constant velocity. Such a system is called an inertial system. So, if this is a primary inertial system, this is also valid here. This is x dash, y dash, z dash, o dash is another reference system that is moving at a constant velocity with respect to this system. This system will be called inertial system. If this x dash, y dash, z dash system is rotating with a constant angular, even at a constant angular velocity with respect to x, y, z, this will not be called inertial system. So, for inertial system, the reference system x dash y dash z dash has to move with a constant velocity or be stationary with respect to x, y, z. So, therefore, the Newton's second law is valid in the inertial reference system, only that type of thing. Now, Newton has provided three laws in his book Philosophia Naturalis Principia Mathematica in 1687. These three laws can be, in a very crude manner, they can be stated like that. First law, an object in motion will remain in motion unless acted upon by another force. Second is force equals mass times acceleration. Third is that for every action there is an equal but opposite reaction. You have been using the first law and third law in solving the problems of statics also, because the first law will require that if the body has to be at rest, then the net forces acting on that will be 0. The second law, second law was not used in solving the statics problem. Third law says that there has to be equal and opposite reaction, that you have used in solving the truss problems. If a truss member applies a force at another member, the equal and opposite force is applied on it by the second member. These laws, in a more sophisticated manner, they can be stated as the first law: if no external force acts on a particle, then it is possible to select a set of reference frames called inertial reference frames, observed from which the particle moves without any change in velocity. So, the first law defines an inertial reference frame. If no, first law says if no external force acts on a particle, then it is possible to select a set of reference frames called inertial reference frames, observed from which the particle moves without any change in velocity. That this statement that it is possible to select a set of reference frames called inertial reference frame, observed from which the particle moves without any change in velocity, indicates that there are other reference frames about which the particle may move without the application of the external force. For example, if you take a cart and this cart put a pillar on which and suspend with a thread a small ball. The ball keeps on deflecting depending on the acceleration of the cart. Although no horizontal force is acting as if a person sitting on it is observing that there is no horizontal force acting on the bar. So, therefore, the first law is valid only in an inertial frame. So, by this you can have this one definition of inertial frame. Now, the second law says that observed from an inertial reference frame, the net force on a particle is proportional to the time rate of change of its linear momentum. That means, in the second law, F is equal to d p by dt, where p is the linear momentum. In classical mechanics, p is equal to mv dt, and if the mass is kept constant, then this becomes m dv by dt, and which is equal to mass times acceleration. This law is often stated as F is equal to ma. This is valid only in an inertial reference frame, and an inertial reference frame is that frame in which if no external forces act on a particle, then the particle moves without any change in velocity. So, therefore, the definition of inertial frame comes from the first law, and the second law shows that the force is equal to mass into acceleration. The third law states that whenever A exerts a force on B, B simultaneously exerts a force on A with the same magnitude in the opposite direction. So, the third law brings into picture the concept of a force. A force can be applied by only some other body. It is not an independent quantity. A particle can have velocity irrespective of any other body. What is happening on the other body is of not concern. A particle can have mass, but the particle cannot have a force acting on it unless there is another body, and on that body also the force will be applied. Therefore, the third law may provide a concept of the force. Force has to be applied by the agent, and it is not an independent quantity. Now, a strong form of the third law says that two forces act along the same line. However, there are cases that in which the forces are same magnitude, opposite direction, but they may not be in the same line, particularly in the current carrying conductors, when the forces, magnetic forces act on them. So, their line of action is different. Now, these in the stating of these laws, there have been certain changes compared to the original laws. So, that means these laws have been put in a refined language over a period of time. Now, This first law originally was stated something like this: an object at rest will remain at rest unless acted upon by an external and unbalanced force. An object in motion will remain in motion unless acted upon by an external and unbalanced force. This law is also called law of inertia. It is our common observation that an object at rest remains at rest unless acted upon by an external and unbalanced force. However, we have it is to see in a subtle manner that an object in motion will remain in motion unless acted upon by an external and unbalanced force. It is not possible to avoid the forces on a moving body. When a body moves, then there are friction, there are wind resistances. So, really that this has not been, any experiment has not been done which shows that a body keeps on moving unless acted upon by this thing. Then second law was stated as the rate of change of momentum of a body is proportional to the resultant force acting on the body and is in the same direction. The exact original translation was like this: the alteration of motion is ever proportional to the motive force impressed and is made in the direction of the right line in which that force is impressed. If a force generates a motion, a double force will generate double the motion. A triple force triple the motion, whether the force be impressed altogether and at once or gradually and successively, and this motion being always directed the same way with the generating force. If the body moved before is added to or subtracted from the former motion according as they directly conspire with or are directly contrary to each other or obliquely joined when they are oblique, so as to produce a new motion compounded from the determination of both. Here one has to see that the Newton has used word motion instead of momentum. Now, the motion, now these are the some changes in the languages of this one rules. Now, we have to understand that the first law and second law, they require the presence of the inertial reference frame. They are not valid in non-inertial systems. Many times mistakes are caused due to the application of these laws in non-inertial system. Therefore, one has to be careful in applying Newton's law to only an inertial frame of reference. We will illustrate the application of Newton's law by one example. Consider pulley mass system. This is a pulley over which the string is passing, then another pulley, then string goes like this, and this is going here, if a force of 20 into 9.81 Newton is applied here, and here this is a mass of 30 kg is suspended from here. We have to find out the acceleration of 30 kg mass when the card is being pulled by 20 into 9.81 Newton force. We neglect friction and the mass of the pulley and then make the free body diagram of 30 kg mass as well as pulley attached to it. Tension in the card will be everywhere equal to 20 into 9.81 Newton because there is no friction present. So, making the free body diagram, we get of the pulley, we see a 30 kg mass is acting here, force is acting here. So, 30 kg into 9.8, that will be the force. So, 30 kg, 30 into 9.81 Newton. T is like this is T. Upward force in this case is 2T. Which is 2 into 20 into 9.81. Downward force is 30 into 9.81. Therefore, net force in upward direction is equal to 40 into 9.81 Newton minus 30 into 9.8 Newton is equal to 10 into 9.81 Newton. Now, using Newton's second law, vertical acceleration is equal to 10 into 9.81 divided by 30, which is equal to 3.27 meter per second square. If instead of applying 20 into 9.8 Newton force like this here, if we hang a 20 kg weight from the free end of the string, will the acceleration be same as before? Intuitive reasoning shows that it will not be, because the extra mass has been attached, which will you have to need some force to accelerate that mass as well. Let us try to solve this problem. This one is and this is pulley here, another pulley over which it goes, and then this is 20 kg. This is 30 kg. Now, making the free body diagram of 20 kg mass, we see that 20 kg mass is subjected to force 20 into 9.81 Newton due to gravity and a force T on upward. Now, minus T plus 20 into 9.81 will be equal to 20 into acceleration of the mass of 20 kg. What is the acceleration of the mass of 20 kg? If the acceleration of 30 kg mass is A, the acceleration of will be 2A. Because if the 30 kg mass goes up by distance of x, the 20 kg mass will move down by distance of 2x, because there are two strings. See, when it has moved at a distance of x, this string has been shortened by length x, this also has been shortened. The same goes here, so 2x. So therefore, this is 20 into 2a, or 20 into 9.81 minus t is equal to 40a. We may make the free body diagram of 30 kg mass, which is like this. That is 2t minus 30 into 9.81 is equal to 30a. Solving these two equations, that is one equation 20 into 9.81 minus t is equal to 40a, other 2t minus 30 into 9.81 is equal to 30a, we get 10 into 9.81 is equal to 110a, or a is equal to 9.81 by 11 is equal to 0.892 meter per second square. So we see that the acceleration has got quite reduced. Similarly, we also will see that from the previous slides that in this case t will be equal to 20 into 9.81 minus 40a. So this will create reduction in tension in a way that then the particle 30 kg mass will experience lesser tension because of the presence of this thing. Now, so this is like that. There can be various examples of applying Newton's law. Now we discuss another principle that is called D'Alembert's principle. Newton's second law is F is equal to ma. We can write it F plus minus m a is equal to 0. F is the resultant of external forces applied on the particle. We can treat minus ma also as a force. Then we can say that the body is in equilibrium under the action of external forces, resultant external forces, and force minus ma. This fictitious force is known as inertial force, and the artificial state of equilibrium created is known as dynamic equilibrium. The transformation of a problem in dynamics to one in statics has become known as D'Alembert's principle. D'Alembert published his work in his treatise De Dynamic in 1743 after Newton. So, this is nothing but the Newton's law stated in other way. So, the problem of dynamics can be solved as the problem of statics. This minus ma can be called as inertia force. Inertia force is a fictitious force. It is not a real force. Assume that if a particle is rotated by in a horizontal plane by means of a string. For an external observer, the particle is moving and it has a centripetal acceleration v square by r. There is a tension T which pushes the particle towards center. So, for an external observer, the particle is moving with a centripetal acceleration of v square by r. Newton's law can be applied and we get T is equal to mv square by r. Now, suppose the observer is sitting in the particle itself. For him, the particle is not moving, but he is seeing that particle is being pulled by a force T. Thus, he will feel that there is an outward force that is balancing this force. This fictitious outward force is called inertia force. So, therefore, particle is balanced due to presence of T and minus mv square by r is equal to 0. You can either apply in Newton's second law or D'Alembert principle. However, we must keep in mind that Newton's second law is valid in the inertial reference frame, and in the same way, so is the case for D'Alembert's principle. We have to be careful. Always the acceleration should be measured from the inertial reference frame. Now, let us do one problem. Suppose you have a cart of mass m, small m, and which there is a crate of mass m. It is being pulled by force P. The coefficient of friction between the crate and cart is mu and 1. That means coefficient of friction here is mu 1. Coefficient of friction between the cart and the road is mu 2. Find out the maximum value of force P such that crate do not slip. Determine the maximum allowable magnitude of P and the corresponding acceleration of the cart. Now we make the free body diagram of the mass, big mass m. Now if we make the free body diagram of the mass m, we see that it is subjected to force due to gravity, that is mg. Then the vertical reaction which is put by the cart on it, that is n. Then there is no force acting in the horizontal direction here, there is only a friction force which may be in this direction, that is F, and then there is a force, then it is accelerating, therefore I can put it inertia force as ma opposite to the acceleration, because if the acceleration is in this direction, so inertia force is ma. F is equal to, now we can apply D'Alembert's principle and consider the static balance of this. We have to understand that here the acceleration A has to be measured with respect to the ground, which can act as inertial reference frame, not with respect to the particle m or cart m. With respect to cart m, the acceleration is 0. So applying where frictional force, vertical force balance gives n is equal to mg. Friction force F is equal to mu 1 times n, applying the Coulomb's law, which is equal to mu 1 times mg. If you balance these two forces, F is equal to ma, that means mu 1 mg is equal to ma, thus A is equal to mu 1 g. So this is the maximum possible acceleration of the cart which can take the mass, big mass m without slipping. Now from the free body diagram of the crate plus cart, m, this is mass m, this is the cart m, this is force n, mu 1 mu 2 n p this is P minus mu 2 m plus m g minus m plus m into A equal to 0. this is MA, this is N, mu to N, P, so P is equal to M plus M into A plus mu 2 times M plus M into G, or this is M plus M mu 1 G plus mu 2 M plus M into G, or M plus M G mu 1 plus mu 2. So this is the value of the maximum possible force P. So this has been done. We will discuss about the work and energy approach and solutions of by impulse and momentum methods in the subsequent lectures. Before that, let us solve some problems which use the Newton's second law. Now a particle, suppose a block, is resting on this one, mass M, and this is a force is applied by pulling it through a rod which is making an angle theta. If the force magnitude is P. Now find out the angle theta, optimum value of that angle theta, which will provide maximum acceleration to this mass. Coefficient of static friction is mu s and coefficient of kinetic friction is mu k. During the motion of the block, only the kinetic force will be responsible. So mu k mg minus p sin theta, because if we make the free body of this one, then there is a force mg, there is a friction force F, then P sin theta, and this is N, I am showing N here. So, and this is P cos theta. So the vertical force balance gives N is equal to mg minus p sin theta. So mg minus p sin theta into mu k is equal to p cos theta, because horizontally mu k is the F is equal to mu k times mg minus p sin theta is equal to p cos theta if there is no acceleration, and if there is acceleration, then pk cos theta, net force is pk cos theta minus mu k mg minus p sin theta is equal to ma, or a is equal to p cos theta minus mu k mg minus p sin theta divided by m. Now, therefore, the acceleration is dependent on theta. Acceleration is a function of theta in this case. Now, if we take for which value of theta the acceleration will be maximum, we have to put dA by d theta is equal to minus p sin theta plus mu k p cos theta divided by m equal to 0, which gives tan theta is equal to mu k. So when tan theta is equal to mu k, at that point that the acceleration is actually that maximum. This we can differentiate dA by d theta once more and confirm that tan theta is equal to mu k provides minima. However, from physical consideration, we can see the minimum acceleration may be provided when theta is equal to 90 degree. That time the acceleration, or even that for that matter, if you know p you apply in the opposite direction, then the block will start moving in the opposite direction. So between 0 to 90 degree, maybe that maxima will be at the kernel. That means theta equal to 90 degree. Now let us see another problem, that if there is a block 20 degree you are having a block 40 kg, it is moving with 10 meter per second. Then this is, you have to find out the acceleration of the block if mu s is equal to 0.4 and mu k is equal to 0.25. Mu s is the static coefficient of friction which decides when the particle is equilibrium. Mu k is the kinetic coefficient of friction, so it should be used when the particle is moving. Now in this case, the net force along this direction, how we can find out this is, let us, if we make a free body diagram of 40 kg mass, we will get reaction, normal reaction of the plane as n, then its weight is acting vertically downward, that is 40 into 9.8. Now there is a friction force which is opposing its motion, that is this F. Now n, since there is no motion perpendicular to the plane, therefore n is equal to 40 into 9.8 cos 20 degree, and therefore the frictional force will be equal to mu k, that is 0.25 into 40 into 9.8 into 20 degree. Another component of the force weight along the inclined plane is 40 sin 20 degree into 9.8. So therefore net force in Newton is 40 into 9.8, 40 into cos 20 into 0.25 plus 40 sin 20 this is 9.8 out. So, therefore, acceleration will be found by, that is retardation, if it is moving at 10 meter per second at this moment, therefore, opposite to the velocity, therefore, acceleration is negative, this is minus 40, and therefore, now if we want to find out that when the particle will stop, we can find out t is equal to v divided by a, and which comes out to be 1.767 second. We can also find out the distance traversed by the particle before it stops by d is equal to v square by 2a. See this another example. This is a cart, and it is being pulled by string. A man may be sitting here and he is pulling the string like this. So it is. In this case, if it is pulling with a force 250, but if we make the free body diagram of the cart, we see there are this 3. If we cut it here, then we see that what t 3t. So, net effect force will be 3t on that system. Therefore, if t is equal to say 200, so therefore 3t. So, 3t minus mg sin 15 divided by m will be the acceleration. If we take one cart here like this, and on this slide a block, if this angle is theta degree and the block which is moving is of mass mg, we will see the force due to gravity along this direction is mg sin 30 divided by m is equal to the net acceleration, that is a cos 30, because if this cart is having the acceleration a, its component along this is a cos 30, and therefore, we get a is equal to, if this theta is equal to 30 degree, a is equal to g tan 30, or if this angle was theta, a would have been g tan theta. So, therefore, you can make a device to measure the acceleration of a moving bus by means of this type of arrangement. Take that a small gadget in which there is a rod's angle can be adjusted, and on there is a block which moves on a frictionless surface. So, there we reduce the friction. Then when this block gets balanced, that time the cart's acceleration is given by A is equal to g tan theta. So by this you can find out the acceleration of this thing. So we have discussed few problems on the application of Newton's law or D'Alembert's principle. Next we will discuss other approaches to find out the problems of